Today we're going to start a new unit about chemical equilibrium. So far we have been considering that chemical reactions happen only in one direction. So for example, that these compounds, the nitrogen tetraoxide, decomposes into two smaller molecules of mononitrogen dioxide. And the fact that we write only one arrow seems to imply that the only thing that's happening is the reactant transforming into the product. However, as the concentration of the products increases, the probability that two molecules may collide with enough energy to react and recombine into N2O4 will get larger and larger, and therefore we should also consider that there is going to be a reverse reaction with its own kinetic constant. So we're going to use the letter R for reverse reaction and the letter D for direct reaction. In this case, these two compounds are kind of relatively easy to tell apart because they have different colors. They are both gases, so we're going to store them into a sealed glass vial. If we have mostly the N2O4, it's pretty much colorless, while the NO2 has a characteristic brown color. If we start from a vial in which almost exclusively N2O4 is present, we will see that the color over time increases. The increase in color tells us that the concentration of the NO2 is going up, but eventually it will reach a steady state and it will stop changing color. If we start instead from a vial in which is prevalent NO2, so it's darker in color, we will see that the color will fade away, but will reach the same steady state as we have seen before. And so this condition of steady state is called in chemistry equilibrium. So it's kind of hard, even if with the different colors, it's kind of hard to actually visualize exactly what's happening. So we can use a similarity and consider to have pennies instead of molecules. So our reagents consist into a certain number of pennies containing two Ermayer flask. And whenever the reaction happens, we are forming products that correspond to transferring some coins from the reagent's flask to the product's flask. So they are still the same pennies as they were before. What makes them reagents or products is just in which flask they are situated. Right? So we are considering that the kinetic constant for the direct reaction is going to be 1/2, so 0.5. And the kinetic constant for the reverse reaction is going to be 1/4, so 0.25. And to make our life simpler, we are considering that both reaction happens with a first order kinetic. So the rate of the direct reaction is directly proportional to the concentration of the reagents. There is no exponent, there is an exponent of 1 just because it's first order, and the value of K is 1/2. For the reverse reaction, we have a K of 1/4, and the rate is directly proportional to the concentration of the products. Now, if we have actual molecule, the concentration would be the molarity of the products and the molarity of the reagent. Here we have coins, so what we will do is actually simply counting coins. At each moment, we can calculate the ratio between the coins we have on this side divided the coins we have on this side. So we are going to call this ratio reaction quotient. So again, for this similarity that we are using, we are just dividing the number of coins on the right, divided the number of coins on the right. If we were talking of a chemical reaction, we would be dividing the molarity. So let's consider in the first example that we have on the reagent side 360 coins, and on the product side we have nothing. So the product flask is empty. What is the quotient? The quotient would be 0 divided 360, that is 0, right? So we have a quotient of 0. So at the first step, we are imagining that the reaction happens through discrete steps. So at each step we can do the math. So each time we have one step, we need to take half of the coins on this side and move them on the product side. And at the same time, simultaneously, we take 1/4 of the coins on this side and we move them back to the reagents. And then we kind of figure out what's the net movement. Why 1/2 and 1/4? Because we have decided to use those as kinetic constant. So for the first step, we're going to take half of the coins in R, so 180, move them to the right, and then 1/4 of 0 is 0, so we're moving nothing on the other side. So the net movement is 180 coins moving to the right. So after our first step, we are going to have 180 coins left on the reagent side, and now we have 180 coins on the product side, so we have the same amount of coins, so the quotient now is 1. Now we're going to prepare for the second step, so we need to take half of the coins on this side, that's 180 divided 290, and we are going to take half of the coins we have here, 180, but only 1/4, because the constant for the reverse reaction is 1/4. So 1/4 of 180 is 45. So 90 going this way, 45 is coming back. There's a net movement of 45 coins to the right. So this leaves us with 135 coins on the left and 225 coins on the right. And the product, the quotient, the reaction quotient, remember that's product divided reactant, so it's 225 divided 134 is going to be 1.8. So what's happening is that the amount of coins on the reagent side is going down. The amount of coins on the product side is going up. The quotient is going up. I mean, starting from 0, it could only go up. Now we're taking half of 135. Now, obviously, eventually we get to the point where we have odd number. We cannot cut in pieces the coins, so we're going to do roundings, rounding up or rounding down. If we happen to have a 0.5, we're going to round it to make it even. So it doesn't really matter as long as we're consistent. The type of rounding we decide to use is not affecting the final result. So we are going to cut in half 135 and make it 68, and 225, 1/4 is 56. So 68 minus 56 is going to be 12. So you see that the net movement is getting smaller and smaller. We started by moving 180 coins, now we're moving only 12 coins. So at the third step, on the reagent side we have 123 coins, and on the product side we have 237. Q is going up, now is 1.9, but the amount of increase in Q is getting smaller, right? So it's getting kind of toward the steady state. With the next step, we are going to take 62 from the left and 59 from the right. So the net is now dropping to only 3 actual net coins moving towards the right. So we go down to 120 on one side and 240 on the other side. The ratio is 2. At this point, the next step, 1/2 of 2 is going to be 60. 1/4 of 240 is also going to be 60. So I'm going to have 60 moving one way and 60 moving the other way, and the net is 0. So at this point, even if I keep moving coins, I can keep moving 60 coins back and forth, but this is not going to change the total amount of coins on the reagent side. That's going to settle on 120, and the total amount of coins on the product side is going to be 240. The actual, if I could mark the coin and make like a dot with a Sharpie, I could see the coins keep moving, going back and forth. It's the ratio that's not changing, but the movement keeps going. Okay, so let's see So we have reached this sort of sweet spot of Q equal to 2. Doesn't matter how we start. So for example, if we start having the same amount on both sides, are we ending up with any different solution? So you kind of got the mechanism, so I'm going a little bit faster. So we take, every time we take 1/2 of the coins on the left side, 1/4 of the coins on the right side, and we move them, and then we see what's the net result. So in this case, if the amount is the same on both sides, the reaction quotient is 1. So we are going to have a net movement of 90 coins to the right. We see that the number of coins on the R side is going down, the number of coins on the P side is going up, and the quotient is increasing from 1 to 1.7. At the second step, we still see a decrease in R, an increase in P, and the quotient is going up to 1.9. And at the third step, we reach the sweet spot of 2. At this point, we have exactly the same amount going back and forth. Consider that there is rounding, right? So even if we started from a completely different scenario, different numbers, different way to distribute the coins between the two sides, we end up with the same value of Q at steady state. There was 2. What was different was the number of steps. It took us 4 steps in the first example. Here it took us only 3 steps. So the amount of time that the reaction took, this reaction, you know, in quotation marks, so this sort of fake reaction that we're using to understand what's going on, to reach the sweet spot that we are calling equilibrium may take more or less time. The farther away you are from the ratio of 2, the more steps it will take to get there, but eventually you just get there. What if we have all coins on the product side and we have 480? Now in this case, the ratio, if you try to calculate with the calculator is going to tell you error because you cannot divide by 0. But we can think conceptually what happens if the number is not 0 but is very close to 0. So when you have a fraction, if the denominator is getting smaller and smaller, the value of the fraction is getting bigger and bigger. And for the denominator that approaches 0, the ratio of 480 divided this number that's approaching 0 will approach infinite. So you have a Q that's extremely large. So again, usual drill, right? We take half of the reagent, in this case is 0, so we don't move anything, and we take 1/4 of the product, that's 120. So now we see that Q is going down. It was infinitely large, so it can only decrease. The number of coins on the product side is going down. The number of coins on the reagent side is going up. By the second step, we have a Q of 2.2, and then by the third step, we have a Q of 2.1, and by the fourth step, we have reached, again, equilibrium, because at this point, we will have 80 coins going in both directions. It's really important that you pay attention to the fact that by the time we are at step 4, the reaction is not done. We can keep moving coins back and forth. It's just that we are moving exactly the same amount of coins in both directions. So what's not changing anymore is the ratio, the number 2. Is not the number of coins on each side is not changing, but the coins are still moving back and forth. Also, I want you to notice that the number of coins is not the same, right? In this particular, depending on the value we pick for K, we have a certain value of Q. So the fact that Q is 2 at each and every time is telling us that the amount of coins on the product side is always going to be, by the time we reach equilibrium, is going to be twice as big as the number of coins on the reagent side. So let's imagine that we start from 480 coins on the product side and 240 coins on the reagent side. So the ratio at the very starting point of the simulation is already 2. In this case, 1/2 of 240 is 120. 1/4 of 480 is 120. So we are already at equilibrium. So that would be like super fast. We are already at equilibrium. This system doesn't have to do much to reach equilibrium. What could be interesting is to think then what happens if now we have an external perturbation. We kind of mess up with the equilibrium, right? Let's consider one last example. In this case, in this scenario, we have on the product side 480 coins, and on the reagents side 240. So it's already in a ratio of 2 to 1. Q is already 2. When we go to calculate the amount of coins that would move from left to right, that's half of 240, so that would be 120. The number of coins that would move from right to left, that would be 1/4 of 480. That's also 120. So the net movement is 0. So we are already at equilibrium. We can keep moving. We can keep going for as many steps as we want, despite coins keep moving back and forth. Because it's the very same amount of coins, the number in each flask would stay constant, and the ratio would be 2. Now what happens? So we are already at equilibrium without basically having to do not to do anything. What happens if something from the outside happen and kind of perturbate this equilibrium? For example, what if I reach with my hand into the flask and I take out half of the coins on the product side? So instead of having the 480 that I had before, now the amount of coins on the product side drops to 240. So in chemistry we call this a perturbation of the equilibrium or a stress. And in this case it's removal of the product. That's something that would often happens in the industry, because if, let's say, I'm in the business of producing ammonia, as I produce it, I want to take it out of the reactor and start packaging and shipping it, right? So as a consequence of this taking away of the coins, the value of Q has dropped to 1 and is now too low, because let's say the steady state, the special, the nirvana value is 2. So what's going to happen is that I'm going to have a net movement, and at the first step you see that you would have 60 coins moving from from reagents to products, so from left to right. As this net movement keeps going, you are going to have less and less coins on the reagent side and more coins on the product side, until the value reaches again 2, at which point the ratio is going to be constant once again. So we started having 240 coins on the reagent side. So again, if my business is to make products and sell them, I have all those reagents sitting there and not reacting because I've reached the steady state and things are not moving. But if I take away all my products, all of a sudden more reagents are going to move. I'm going to have a net movement into the product side, and I've been able to use, let's see, instead of having 240 coins sitting in the reagent flask, now I have only 164. So I managed to mobilize more of my reactant and make more of my product, let's say ammonia. So this is an effective way to increment the yield of products that would otherwise be sort of stuck by the equilibrium, by the type of equilibrium that I have. So because my Q is 2, I can only have that much products. But if I keep subtracting, taking away the products, I can drag more reagent on the product side, basically. So we have seen that there are many value of Q's, one per each example that I gave you, I mean by the initial, right? So, and Q was changing over the experiment. So Q can have any value. There are infinite value for Q. And we calculate Q as the ratio between the products and the reagents. However, there was only one sweet spot where the reaction would reach a steady state. And that value was a constant. And it would stay a constant and as long as I don't change this value. If I would, start everything again by changing these numbers, then I would get to a different sweet spot. But as long as KD is 1/2 and KR is 1/4, Q is always going to try to reach that sweet spot of 2. So that value, because it's a constant, we are going to use a special symbol, and we're going to call it KAQ. So there is only one value, but it's also the ratio between products and reactants. So this is sometimes a little confusing for the student because it seems like the same formula is giving you two different things. But Q means, any value that that ratio could assume, while KQ is a specific value that is characteristic of each reaction. And if you notice, 2 correspond to dividing 1/2 divided 1/4. This is a special case because everything was first order, all the reactions were first order. That's not generally the case, but in this case it happens. So you can see by changing the ratio of those two numbers, I can get a different value of equilibrium constant. So the take-home message is that there is one and only one equilibrium constant value, but there are infinite value of Q. We will go over this again, but just it's trying to kind of nail the most common misconception, right? So let's go over a summary. By the time you reach equilibrium, so this steady state, what is equal, there are certain things that are equal and certain things that are not, and students tend to confuse those. And because they are common misconception, that's what they always ask in tests and finals. So it's really important that you don't fall for that, right? So what's going to be equal is the rate of the direct reaction, the number of coins that are moving in each step one way or the other. That's when you have equilibrium, you have the same number of coins. Also, at that point, obviously the concentration of R and P are going to stay constant. Therefore, the ratio is going to stay constant. The ratio is not typically 1. It could be, but it's kind of a rare situation actually. So typically, R and P, by the time you reach equilibrium, are two different numbers. So in our case, one was always twice as big as the other. So the concentration of reagent and product typically is not the same at equilibrium. At other common misconception, at equilibrium the reaction does not stop. You keep moving the coins, it's just that you are not changing the absolute numbers. So it's a dynamic equilibrium. The equilibrium can be reached from any side. So we started by having exclusively reactant, or we started by having exclusively products, we started by having 50-50, we have always ended up at the same point. There are infinite values of Q, but there is only one value of the equilibrium constant. The only thing that would change the equilibrium constant is changing those kinetic constants, right? And what does change the kinetic constant? Temperature. So the only factor that would affect the value of KQ is a change in temperature. So now it's time to watch a movie. And so go and watch the video on YouTube, and then we can meet again for another PowerPoint presentation. Stay safe.